Hello guys, welcome to all of you. Let us see another question on Thevenin's equivalent circuit and find out the Thevenin's resistance in this circuit. This is the question of GATE 2023. In this question it is said that using incremental low frequency small signal model of the MOS device, the Norton equivalent resistance of the following circuit is. In this question, Norton equivalent circuit resistance has been asked, but we will solve this question to find out Thevenin's equivalent resistance. And as we know that Thevenin's equivalent resistance and Norton equivalent resistance both are same by calculation, and the value of these two resistances are same. So let us see how can we solve this question. First of all, let us see that how can we convert a MOS device into a low frequency small signal model. As we know that MOS device is a two-port network. As here we can see that this is the input port and this is the output port of the MOS device. Now if we convert this MOS device into low frequency small signal equivalent circuit, then we can see that this terminal is VGS, here is gate, this gate is here. As we can see in the question that gate is grounded, so we have grounded the gate, so VG value will be 0 in this question. This is the gate voltage. Here VGS is voltage between gate and source, and this is the source voltage. In equivalent model of low frequency small signal of MOS device, we connect a dependent current source GM VGS at the output node, and RDS resistance between drain and source, that is RDS, which is connected here, and this is the drain and this is the voltage at the drain. So this is the low frequency small signal model of MOS device. Now let us see how can solve our question. Now we have connected this equivalent circuit of MOS device to find out the Thevenin's resistance of the circuit. In this question we can see that a test voltage is applied at the source, as we have to find out the Thevenin's equivalent resistance at the output port. So here test voltage has been applied at the source, and this ground is connected to this ground, so this is the output port and this is the input port. So in this question, as we can see that in the equivalent model of the circuit, as we can see that there is no independent voltage source applied in this circuit, so we will find out this Thevenin's resistance of the circuit by using the second method, where only dependent source is connected to the circuit. So for this sake we will apply a test voltage and find out the Thevenin's resistance. We have applied a test current source here, and assume that voltage across this test current source is V test. We can apply the test voltage source here also, but for the easy calculation we have to see that whether we apply voltage source or current source by which our calculation can be minimized. So we can see that most of the MOS devices, if we connect a test current source, then calculation will be easy. So here we have applied a test current source and assume this is 1 ampere, as we have seen in our last videos that we can assume it 1 unit source, so that our calculation will be easy. So voltage across this current source is test, V plus minus V test, and if we see that this 1 ampere current will flow towards this node, we have seen in our equivalent model that this circuit is open and across this voltage is VGS, so there will be no current flow towards this direction. Then whole 1 ampere current will flow in this direction only. Here GM into VGS current, dependent current source, will give current in this branch 1 plus GM into VGS. So the total current flowing through RDS is 1 plus VGS, 1 plus GM into VGS. Now at this node we can see that total current 1 plus GM VGS come towards this node, and GM into VGS current will flow outwards from this node. So if we apply KCL at this node, then we find that towards this branch we find 1 ampere current. Now if we see that VGS is equal to minus VS, if we apply KVL at this input port, then here we can see that KVL at input port, here if we move from gate towards the source, then we find out that the second sign is minus, so minus VGS. Here we have written minus VGS, and in this node we can find out voltage source VS equal to V test voltage. So if we write KVL, then moving towards this node we find plus VS here and minus VS here. The second sign is minus, so here will be minus VS equal to 0. Now we can find out Vs is equal to minus VGS. From the circuit we can see that Vs and Vtest voltages are same, so Vtest is equal to minus VGS. So VGS can be written as minus Vtest, and we have assumed it equation number 1. Now if we apply KVL at output load, then we can see move from source toward the drain, then we can find out here is a test voltage, so second sign is positive, we have taken plus V test here. And now if we move towards this node, then we find out that 1 plus Gm VGS current will flow to this RDS resistance. Then we can write as minus 1 plus Gm VGS into RDS, voltage across it. And if we go towards the load, then we find out that 1 ampere current flow toward this R resistance. So it will be minus 1 into R equal to 0. If we rearrange this equation, then we will find out V test minus 1 plus Gm and VGS value can be written from this equation number 1. Then we have put VGS equal to minus V test here, and into RDS equal to R. If we solve this question, then we find V test is equal to capital R plus RDS whole upon 1 plus Gm into RDS. As we know that Thevenin's resistance RTH and Norton resistance Rn can be calculated by same method, so its value will be equal always. We will see in our Norton's theorem that how can we solve this resistance Rn. So we can say that RTH is equal to Rn is equivalent to each other, so the value of these RTH and Rn will be equal, and these values can be written as V test upon I test. So V test and I test we have assumed here 1, as in this question. Here is the I test is equal to 1. So its value, RTH value will be V test. So RTH is equal to Rn can be written as V test value we have calculated here, capital R plus RDS whole upon 1 plus Gm RDS. So this is the equivalent Thevenin's or Norton resistance of this MOS resistance. So we can calculate any MOS circuit by applying this kind of low frequency model of small signals and find out equivalent resistance of the circuit. Sometimes we need to calculate the RTS for the calculation of the voltage gain of the circuit. So where MOS is connected, if we want to find out voltage gain of the circuit, then we have to apply this kind of Thevenin's equivalent resistance or Norton equivalent resistance, and after applying it we can find out the voltage gain of the circuit also. So this is the very important method, and we should know that how can we solve a MOS circuit by using small signal low frequency model of the MOS device.